Hello all the crazy people out there, my name is Michael, I like wizards and dragons and making games, and recently I made a video on sprite packing. So sprite packing is the name of a family of techniques used in taking a bunch of sprites of varying shapes and sizes, at least usually, and putting them together so that they can be packed into some space, usually for the purpose of creating a texture atlas or a sprite atlas or something to that effect. So in the first video I made on this, our algorithm wasn't all that sophisticated. We just basically took all of our sprites and lined them up and put them into either a linear strip initially or later on into a grid like this. And it's okay, it gets the job done. It was fairly simple to write, it's fairly quick to compute, but we can see just from looking at the results that it kind of wastes a lot of space. And in fact, I added a little bit of additional information to the top of our screen here. So we've got the dimensions of the final atlas, which is 800,768. We've got the area of our final atlas, which is about 600,000 pixels, and we've got the amount of this atlas which is actually covered by one of these sprites, which is 48.91%, or a little bit less than half, as well as the amount of time that it takes to compute this. So a little bit less than half isn't really a great ratio for sprite packing. A lot of the more battle-tested sprite packing algorithms out there will probably hit 85-90% in most cases. Maybe a little bit more if you really squeeze in a lot of little ones. So we can definitely improve on this. I want to say the algorithm that I'm going to be going with today is going to hit about 80% or so. We are going to want to pay attention to the build time here, because sprite packing is one of the many things in computer science where there's a trade-off between the amount of memory that it takes to do something and the amount of time that it takes to do something. So it's pretty easy to write a very naive sprite packer that wastes a lot of space. But doing one that is much more spatially efficient is going to take a lot more time, both your time writing the code and also time for the computer to carry out. And one of our jobs today is going to be to figure out a nice trade-off between space and time. Because if you're going to be using this in a game, you most likely don't want to have to make the user just sit there for like entire seconds or even minutes at a time while this thing carries out. All right. So in this project, we've got pack sprites v1 and pack sprites v2. As I said, they're not that sophisticated. They just take a bunch of sprites as an input array and just like lay them out end to end. I'm going to control D duplicate this. I'm going to go say pack sprites v3, and that's going to be what we work on today. Let's rename that pack sprites v3. I'm also going to go into the creative end of our object here, and I'm going to actually call that version of the code. And now we can jump back here and we can start ripping pieces out and rewriting them. So what is this algorithm going to look like? So I guess I'll run this again so that I can like point at things with my mouse cursor. So instead of just arraying all of these sprites one by one in a series of rows and columns like this, what we're going to do this time is we're going to start for every sprite in the list. We're going to start in the upper left corner. We're going to check if there's an overlap between that sprite and all the other sprites. If there is a collision, if there is an overlap, we'll move over 1 pixel and then we'll check again. We'll keep doing that until we find some empty space. If we hit the leftmost side of the sprite atlas, we're going to move back to the beginning, move down 1 pixel, and we're going to keep going. So we will scan column by column, row by row until we find empty space. This means a few things. For one, this means that smaller sprites will sometimes be able to fit in space left by larger sprites, which is a trait that you usually want from a sprite packing algorithm because that's what leads to more efficient use of space. And it also, if you are keeping score there, it means that we're going to have a total of 4 nested loops going on here. So this is not exactly going to be a fast operation, but we will do some things towards the end of the video to speed it up considerably. And there's a whole bunch of different sprite packing algorithms out there. I probably saw 5 or 6 viable ones when I was looking around the internet for things to do with this video. And I'm sure there's many, many more that are floating around out there that are more niche or don't work as well or only work under certain conditions or that kind of thing. So let's get started. I'm going to start by cutting out a lot of the stuff inside pack sprites v2 that we didn't really need. So there's actually, now that I look at it, not quite as much as I thought. So all of this stuff between the beginning and where we create like the sprite atlas surface, I'm gonna get rid of. Down here, inside the loop where we draw the sprite, I'm going to get rid of everything that isn't like this. I'm going to get rid of this atlas metadata array, and I'm just going to return... I'll leave the rest of it alone for now. We'll come back to it later when we actually get to drawing the sprites that have been placed somewhere on the image. Just decluttering this a little bit. So V2 started off by figuring out the largest width and the largest height of all the sprites in the array. I am going to want that eventually in V3, but I'm not going to want it yet. I will come back to it towards the end of the video, and I don't feel like deleting it and then rewriting it, so I'm just going to leave it there. The other thing I'm going to want is to go alongside our array of sprites. I'm also going to want an array of basically like bounding box information for all the sprites, so where they're actually located in our atlas. So in earlier versions, we just computed that on the fly in doing some math to come up with a row and a column and a x and a y coordinate. We're not going to do that this time. We're actually going to need to keep track of the x and y positions of each sprite so that we can figure out overlaps and stuff. So I'm going to say sprite rectangles equals array create based on the number of sprites that we have. And then when we iterate over them, we can figure out the largest width, height, whatever. And we can also say sprite rex index I is going to equal a struct, which is going to contain x initialized to 0, y initialized to 0. Width is going to be sprite get width. Height is going to be sprite get height. And I'm also going to want a little boolean true or false placed, which I'm going to initialize to false. That's just going to be a little variable which we'll use to figure out if a sprite has yet been placed in the array or not, on the atlas or not. We'll get to that later. Okay, so some more setup that I'll want is going to be, I'll want to I'm going to want to initialize the atlas width to something. In V2, our sprite atlas width was based on like the square root of the total area of all the sprites so that we could hopefully kind of sort of maybe make this like a square, more or less. And the way that we figure out the atlas width and the atlas height is going to be kind of like that in V3, but I'm just going to hard code it to 1000 right now because that's going to be good enough. Later in the video, I'll come up with a more programmatical way of working that out. And I'm also going to say atlas height can be initialized to 0. So I'm going to give this sprite atlas a fixed width, and it's going to grow downwards as more sprites are added to it. Like I said, there's a bunch of different sprite packing algorithms out there. Some of them handle this in different ways. I think GameMaker will start with like a 1x1 image, and then it will grow it both horizontally and vertically. But I think that's a little bit too much math for me right now. And I don't think doing it like this is going to make the whole thing that much less spatially efficient. So for the sake of keeping this a little bit simple, I'm going to give it a fixed width and I'm going to have it grow downwards. Next, it is time to start writing some for loops. So we can start by iterating over every sprite in the list again. By the way, it is possible to do this with sprites that have multiple frames and then to also atlas the individual frames within. I'm not going to do that here. It's really not that hard to take this and adapt the code to make it work like that. You basically have to create separate definitions for each individual sprite frame that you want to add. But I already foresee this video being like way too long, and I don't really want to add that on top of it. Anyway, so we're iterating over our sprite count. I can say var this sprite equals sprite rex index I. So we're going to start by taking the bounding box information for each sprite, and we're going to try and place it. So now begin the really insane loops. I'm going to start out by saying var y equals 0, and this might look a lot worse than it really is, but I'm going to say while true y plus plus, and this is going to be our moving down the image vertically. We will check every row in the sprite atlas to see if there is any free space for the sprite that we're trying to place. If there is, we'll place it. If not, we'll move down to the next row. Inside this infinite loop, we're going to create another loop. I can say for var xx equals 0, xx is less than atlas width xx plus plus. And this is going to have us iterate over every column horizontally. I am going to want to say if xx is less than atlas width minus this sprite dot width, because if I don't do this, it will be possible to place sprites like on the end of the image, kind of hanging off the side, intersecting the rightmost boundary of the atlas, which we don't really want. So this will just make sure that there is enough horizontal space on each column to actually place the sprite down without like going overboard. Anyway, that is our third nested loop. the last loop I'm going to want is I'm going to want to check if there is a collision between this sprite at this position with any of the other sprites that have been placed. So now, for the grand finale, for var j equals 0, j is less than sprite count, j plus plus. We can iterate over every sprite again. Let's say var that sprite equals sprite rex index j, not index I. Made that mistake before. We can say, how about var overlap equals false? So we'll start by assuming that there is no overlap between any of these other sprites and this sprite. And then we're going to... Actually, I want this to be outside. I want this to be in the... in this level, right underneath the for x equals 0, x is less than whatever. So we're going to start by assuming that no overlap is found. We can figure out if an overlap is found by doing a little rectangle check. And you can do this yourself manually by doing things like checking if like the left side of this sprite is greater than the left side of that sprite, but less than the right side of that sprite. That's going to be a lot of writing. It's going to be surface area for bugs to sneak in. I don't really want to deal with that. It's also going to be a little bit slower than just letting GameMaker use the rectangle in rectangle function, which is a function built into GameMaker that will do the exact thing that I just said. This is a function which will take 8 numbers as an input, the 4 corners of one sprite, the 4 corners of another, or the bounds of one sprite and the bounds of another anyway. And let me give these values names that might sound something like this. x1 is going to be this sprite.x, var this x2 is going to be this sprite.y. This y1 I want that to be. Var this x2 is going to be this x1 plus this sprite.width, and this y2 is going to be this y1 plus this sprite.height. And we can do the same thing for that sprite. So we've got that x1, that x2, that y1, that y2, and we're going to want to make sure that we're looking at the correct sprite. Otherwise, things will end up in the wrong place. Rectangle and rectangle, starting with this x1, this y1, this x2, this y2. And then the second rectangle is going to be that x1, that x2, no, that y1, that x2, that y2. And then if this condition is true, that means that an overlap has been found. Hello. That means that an overlap has been found. We're going to set overlap to true. And we can break out of this j equals 0, j is less than whatever loop, because we don't need to search anymore. That's already been found. And once we're done checking every one of these sprites, by the way, the other thing we'll want to do is we'll only want to do this if that sprite.placed is true. So if that sprite has already been placed inside the atlas somewhere, it doesn't make any sense to check this sprite against a sprite that hasn't been placed yet, because they will all default to like 0, 0 at the upper left. And I guess in some ways you could initialize like x and y to negative infinity or something like that, but we're just going to use this little placed boolean. All right, so once we're done with all that, if no overlap has been found, so if not overlap, then we can declare that the sprite has enough free space to be plonked down. We can say this sprite.x equals xx, this sprite.y equals yy, this sprite.placed equals true, so that it will be registered in future checks with future sprites. And I'm also going to take the atlas height that we initialized to 0, and I'm just going to say atlas height equals the max of atlas height, and this sprite.y plus this sprite.height. And that's just going to keep track of the bottommost extent of the bottommost sprite, so that we know how big to make the sprite atlas surface when we go and actually draw the thing. All right. So what level of the loop are we in? We'll also want to break out here if an overlap is found, because if an overlap is found, you don't need to keep scanning horizontally. And also, at the end of the horizontal scan, inside the while loop, right above y++, we can say if this sprite.placed. We can break out here too. A lot of people, including me, have asked GameMaker for like a multi-level break expression so that you can, like, if you're inside a nested loop like this, you can just break out easily. But it's not a thing in GameMaker, unfortunately. And honestly, GMRT, I don't know, maybe depending on what other languages we get access to in GMRT, we'll just be able to use another language if we want that. So that's going to go and place all the sprites. So once we've run this, it should work just fine. We will need to actually draw these on the Sprite Atlas surface here. So we're going to iterate over our list of sprites once again. So sprite is going to equal sprite rex index I. We'll want, I call the sprite info equal sprite rex index I, because saying like sprite.sprite looks stupid and it's easier to lose track of what's going on. I'm going to say sprite info.sprite. Subimage 0, again, if you're accounting for different sprites with multiple subimages, you can handle that yourself here. Sprite info.x, sprite info.y. After that, we can reset our target, create a sprite from that surface. That's going to be our like mega texture, our atlas. The metadata, I'm not doing anything with the metadata in this demo, but it is something that's generally useful to have, so I want to include it anyway. And I think instead of just saying the atlas metadata array that we wrote in v2 and then deleted, we can just return sprite rex as our metadata here. And now if I run this for the first time in, what, 20 minutes, the game is going to hang for maybe 10 seconds or so. But once it's done building the atlas, unless I did something incorrectly and it went into an infinite loop, let's see if there's anything obviously incorrect here. Oh, you know what? Initializing this x1 and this y1, this should be initialized to xx and yy, because xx and yy are the actual coordinates that we're checking. And at this moment, this sprite.x and y are always going to be 0, so we're never going to like actually check any different location when we do that. All right, let's try that again. Of all the things that could have gone wrong the first time I ran that, that wasn't that bad. And what don't you like about that? Sprite info.sprite. So we got through all the hard work, and then when we actually went to draw this, sprite info.sprite, did I like misspell something? Oh, I didn't actually attach a sprite to this. When I like set up my metadata down there, up here at the top. Okay, let me run that again. That's going to take however long that took to do the first time, 10 seconds or so. And this says this is run. It took 10 seconds and 808.83 milliseconds, so a little bit longer than I said, but we have gone and packed all of our sprites. We can see that this is taking up much less space than it was the first time. There is still a little bit of awkwardness, and that is because all of the sprites that we're placing down are happening in a more or less random order. I don't know if actually random or if I just... I didn't shuffle the array, which I thought about doing to add some more randomness into like exactly what it is that we're atlasing, but this is just all the sprites in the order that I wrote them down. We can definitely see that it's better, so our total area for this atlas is 444,000 pixels, and our packing efficiency is now 67%, up from 50%. But we can see that there is still obviously a couple of obvious gaps in here which we might want to insert sprites into to save some space. And did I actually talk about this? I don't think I actually talked about this in the first video when I did V2. So it's pretty common when you do sprite packing to actually go and sort your sprites according to some heuristic before you begin. Usually that's going to be by height. You can also use sorting heuristics like sorting them by width, or sorting them by area, or sorting them by perimeter, that sort of thing. So if I do that here, I'm going to drop down a few lines after our sprite rectangle metadata was initialized. We can call the array sort function in GameMaker on the sprite rectangles array, and this is going to take a, or at least we can give it a function to compare two values, A and B. So that's going to be two values that you compare. You're going to want it to return +1, 0, or -1, depending on which one is going to come first. To sort them by height, I'm just going to return the sign of b.height minus a.height. I'm not going to get too into how array sort works here. It's part of the array functional programming set of functions that GameMaker contains. Very useful for stuff like this, to be able to sort an array according to any heuristic you want. Anyway, if I run this now, our packing should be a little bit more efficient, and it should take a little bit less time, because we're going to do basically the hard parts first, and we won't have to check quite as many positions. So that completed in about 8 seconds, and now our total area is about 360,000 pixels for a total efficiency of 82.78%. Definitely better than what we had before. This is a little bit more than half the size of our original Sprite Atlas. V2 was about 600,000 pixels and about 50% spatially efficient. And we can just see visually by looking at this that this is a much better use of space. And it helps, admittedly, that a lot of these sprites are sort of the same size. I just pulled random sprites from Wizarducks. I didn't really try to go with a completely random array of sprites or anything like that. So we don't have to do anything really weird fitting sprites into places like L blocks and Tetris or anything like that. We've got a couple of things like that, like this tall grass over here on the side and this short grass over here in the middle, sort of wedged in between there. But for the most part, we've got the large sprites on top and the small sprites on the bottom. And honestly, for this particular collection of sprites that we're trying to sort, I don't know if it's actually possible to do any better than this, just because of the size and shape of the particular sprites that we're trying to sort here. So that still leaves the issue of how this is taking 8 entire seconds to pack all of these sprites into this rectangle. So I have 2 major optimizations for this. Actually, you know what? Let me go and make a commit here. And I'm also going to take this, duplicate it again, and say this is going to be v3a. And we'll leave it before and after here just for posterity. Let's go into the create event of this object that's running this and change that over to use3a. So I have 2 major optimizations for this. One is that we are checking every single pixel, and this will give us pixel perfect packing, but it also means that we have to check every single pixel. And a lot of the times, like, the smallest sprite in this collection is, I want to say, like, 16 by 16 or something like that. This one, what's this one? 3232. So pixel perfect packing isn't possibly all that necessary. We could probably get away with checking, instead of every single pixel, checking like every 4 or 8 pixels or something like that. And this is something that you will commonly see in a sprite packing algorithm. I'm going to define another variable. Let's call it var stride equals 4. And instead of going, when we iterate over our position, saying x plus plus, we can say x plus equals stride. So we're going to go check 4 pixels by 4 pixels instead of 1 by 1. Down at the bottom of this loop, y plus equals stride. And this is going to let this run quite a lot faster. So that was down from 8 seconds to a little less than half of a second. And that's I think that's going to be about a 20x improvement. And our total sprite packing efficiency has gone down from, what was it, 82.7 to 82.1%. So we've lost almost nothing there. We could increase the stride to a larger value, like 8, and we should see correspondingly larger gains. So we've now gone down from 400 milliseconds to 122 milliseconds for another about 3.5x right there.
Hey.
So that's a very easy modification to make to sprite packing algorithms to speed them up if you're trying to do something like this. Here, if you were to, like, arrange these by hand, it is possible to do better by, like, taking these grass sprites, dropping them over here, by taking, like, this long flower sprite, dropping it over there, and then you can sort of squeeze these 2 trees over and save a little bit of space. But 79.5% efficiency is pretty good. And this is now running something like 60 times faster than our original version, which I think is definitely a win. The other thing that you can do to make this faster, and this is actually going to be a little bit GameMaker specific. So if you were to profile this, you would find that a lot of the time that it takes to compute this is going to be between, like, here and here, where we're checking for overlaps, because this is one of the, this is the 4th tier of the system of loops that's 4 levels deep. And this loop is going to run a ton of times every time you run this algorithm. And it would be nice if there was a somewhat faster way to check if there is an overlap between this sprite and all the other sprites. And this is going to be something that's a little GameMaker specific, but GameMaker has a pretty robust collision system. I'm going to make myself a little object to call obj underscore pack sprite 3a placeholder. And I'm going to create a little sprite to go with that. So let's call this SPR pack sprite 3a placeholder. And I'm going to make this a sprite that is going to be 1 pixel by 1 pixel, and it's going to be completely white. We don't really need it to look like anything, we just need it to exist, and more importantly, we need it to have collision information. So the collision mode is going to be set to automatic, type is a rectangle. And we can set our sprite pack 3a placeholder to that object. So we can actually use GameMaker's collision checking functions to speed this up quite a bit. So when we start a round of the outermost loop, so this sprite equals sprite rex index I can save our sprite test instance is going to be equal to instance create depth. I'm going to just create it at 0, 0, 0, and the object is going to be the one that we just made, so pack sprites 3a placeholder. And I'm going to give it some, alright, if you've never seen that before, GameMaker variable definition structs are occasionally handy, but for the sake of simplicity, I'm just going to say sprite test inst dot image x scale is going to be equal to sprite dot width. We can say same thing for image y scale. Like this, that's going to be sprite dot height. That is apparently the wrong variable. This sprite dot width and this sprite dot height. So this is going to be an object whose only purpose is to exist and to check for collisions. There is going to be one associated with every sprite that has been placed. And now, inside our for loop here, where we iterate over every position horizontally, I'm going to get rid of all of this. Actually, I leave the overlap, the overlap boolean over there. I'm going to get rid of all of that. I'm going to say with the sprite test instance, if place meeting, the x position is going to be xx, y position is going to be yy, and the object that we're testing against is going to be every other object that might or might not exist of obj pack sprite 3a placeholder. I could have chosen a shorter name for that. And if we find a collision, we can say overlap equals true. That's going to take the place of the utter nonsense that was the rectangle and rectangle check that we wrote out the first time. It's going to come out with the same value, and if I were to now run the game, we could see that something has gone wrong. Okay, what did you not like about that? I feel like I probably, when we test for collisions with this sprite test instance, its actual XY position in the room is still like 0, 0, where it was instantiated. We haven't actually moved it yet. You could either say sprite test instance.x equals xx, y equals yy like this, and then just check for collisions at xy like that. You could also arrange this some other ways. You could, like, where did I go? You could move this around. Set the position down there. It doesn't really matter. I feel like this, I feel like that's probably better for readability, so I'm gonna go with that. And now, okay, that looks correct, but why are there... Oh, I know why. I'm not actually deleting these, am I? So yeah, when you're done with this, instance destroy all of those, because otherwise they will just hang around in memory, and they will sit there doing nothing. They might interfere with future sprite atlasing invocations if you try to run like multiple of these in a game and don't clean up after yourself. And they might interfere with other things in your game if you're doing anything like solid checks or whatever. Anyway, so from the last time we ran this, we are down from 120 milliseconds to atlas this to 28 milliseconds, so this is about 4 times faster than it was before we started messing around. And I don't even want to think about how many times faster versus like the original version of this code. So let me see. This recording is going to be going on for quite a long time, and I don't even want to think about how much time this is going to take to edit, but there are a couple more things. I did say that I would come back to Atlas with, and like how you figure that out is again kind of up to you. I'm going to go back to what I did in V2, and I'm just going to keep track of the area. So I can initialize area to 0, area plus equals sprite get width times sprite get height. I am writing that out quite a few times here, aren't I? You can turn that into a variable if you'd like, I suppose. So that's going to get the total area of our sprite atlas here, and it might make sense for the width to be something like rounded up to the nearest power of 2, because oftentimes it makes sense for sprite atlases to be of a power of 2 in size. So to work that out, we can take the square root of the area. So if you were to take the area and turn it into a perfect square, it would be of this size. We can figure out the log base 2 of that. We could round that up with a ceiling function, and we could raise 2 to the power of that, and that will basically round atlas width from the square root of the area for like a perfect square to the nearest power of 2 rounded up. So if the square root of the area is like 700 or something like that, it'll turn out to be 1024. If the square root of the area is like 400, it'll be 512. You get the picture. And we can also do the same thing with atlas height at the bottom. Again, because it is often a good idea to have these things be a power of 2 if you're doing these, for like 3D or something like that. It doesn't have to be strictly speaking, but it does make a few things easier. Is that the correct number of parentheses? It is. So now if I run this, we can see that these sprites are packed into a 1024 by 512 area. Our efficiency has gone down because there is wasted space at the bottom, but that's only there because this is, we're now requiring it to be a power of 2 in size. This might be something that you consider making, like, an option if you were to implement this yourself. Another thing, which I said I would circle back to, is the largest width and the largest height. And that technically could be a problem with V2 of the sprite packing algorithm, the other sprite packing algorithm that I wrote a while ago. If the largest sprite maybe is really long but really short, so its width comes out to be more than the calculated width, and it would be a good idea to maybe account for that. So if we say our atlas width equals the square root of the area, we can also say that, just as a sort of safeguard, the maximum of the square root of the area, so our idealized side length and the largest width of any individual sprite, just to make sure that there are no sprites that are longer than our atlas width. So this would have made things a little bit awkward in V2, but it wouldn't have broken the algorithm and made your game get stuck in an infinite loop. But doing so here actually could make your game get stuck in an infinite loop, because basically this would never find a valid overlap region, and it would y would continue to go down infinitely, and your game would get stuck. That shouldn't make a difference here. Yeah, this came out packing exactly the same as it did before, but if I had, for example, a really, really long sprite that was imagine 2,000 pixels long, then that would be a safety check that you want to have in place. And lastly, so this is something that could have been a problem technically for V1 and V2, but I just forgot to address it. So sprites are allowed to have different sprite origins. So if I were to take one of these cards and set the sprite origin to I don't know, the middle, something down in the middle of nowhere, like that, one of those clouds maybe. If I were to run this, we would see that one of these is not getting placed correctly. There is space for it, but it is offset by the amount of whatever the sprite origin is. And that's because when you just say draw sprite at a position, GameMaker will make use of the sprite origin, and it could be shifted over in one direction or the other. And we are going to want to account for that by adding in sprite get offset. What is it? Sprite get x offset of sprite info.sprite. We're going to want to add that sprite x offset into the x position, and we're going to want to add sprite get y offset into the y position, and that is just going to make sure that this draws everything at the correct position no matter where the sprite origin is set. Okay, that's sprite packing. That took a really long time. I'm going to make another commit. And I think I'm going to end this off here. That was a lot of fun. My name is Michael. I like Wizards and Dragons and making games. If you want the code for this, look for the GitHub repository down in the description of this video. This will be coming up again in future videos. I'm not going to look at any other sprite packing algorithms, but the concept will come up again in future videos, so, well, I hope you had fun. You should all go check out Wizarducks and the Lost Hat, which is one of the games that I like to work on when I'm not doing YouTube stuff. Link to the Steam page can be found down below. I have a Patreon, so if you want to contribute to the channel, links to that can be found in all the usual places. I hope you all found that useful, and I will see you all later. Special thanks to Zenjamin, Zach Robinson, Squarecrow, Spy Games, Pixelated Pope, Mantaray, GameMaker, GameMart Indie, Edward Holt, DJ Gibbles, Brenton, and Boketa for supporting these videos. If you want to contribute to the channel, head on over to the Patreon page down in the video description to join the fun.